The question is this. Whether our ontology is non-duality, which for me, I think that non-duality is the best ontology for scientists, because implicitly most scientists, I mean, I'm talking not about engineers, scientists, they have this intuition that there is a global entity called nature, the laws of which they study. And so this intuition is there of a common reality. And to say that there is only one reality without further ado seems to be the most logical, the best fitted ontology for scientists, more than any religious form or atheist form.
Nothing else is viable.
Right. Now, so that being said, that's for the comfort of the scientists, right? But that being said, the question then is, if we adopt this ontology instead of religious or other atheists, other ontologies, does that make a shred of a difference in scientific progress? In other words, is the way, and I'm talking mostly about physics, right? The way physics progress or will progress in the future, does it change at all? It seems to me that within the current parameters of physics, and of science, it doesn't change. It doesn't make any difference. In order for that to make a difference, we would have to enlarge the box of the scientific method. What do you say? What do you say to this?
I think you're correct in principle. I think the methodologies of science are metaphysically agnostic. Science study what nature will do next. It makes predictions about nature's behavior. It doesn't need to go into the question of what nature is.
Exactly.
Because that's not accessible to the experimental method anyway. An experiment is a question of behavior that one poses to nature. That's what an experiment is. So these are the circumstances, and I want to know what will you do next. And then nature answers by doing something in response. It's always a behavior. It's never an unambiguous answer of what nature is. And according to the scientific method, you do not need to know or speculate about what nature is. It doesn't matter. Yeah, it's always a matter of, can you predict what will happen next? That's the only thing that counts. Where I would be more cautious is science is done by scientists, and scientists are human with prejudices. And I think there, one's metaphysical prejudices can lead to tunnel vision. Like there are certain things you will not experiment with because your metaphysical prejudices already inform you that they cannot be true anyway. So why will you bother to look, right? Well, if you looked, maybe you would find some surprises there. Another way in which this human prejudice can happen, and I'll give you a real life example. In foundations of physics, every experiment that was done to try to answer this question since the late 70s, so it's been almost 50 years, every experiment suggests very strongly that physical things don't exist until they are observed. Before they are observed, we cannot speak of defined physical properties. And that comes from entanglement experiments where you have, say, two photons, they are created together, so they are entangled, and then you shoot one to the right and you shoot the other to the left. And then photon A, after a little while, gets measured by Alice, and photon B gets measured by Bob. And it turns out that what Alice chooses to measure about photon A, even if Alice only makes that choice when the photon is already in flight, already separated from its twin, the photon is already in flight, only then Alice makes a random choice of what it Alice is going to measure, like the angle of polarization, which can be any of a number. Alice's choice of what to measure will determine what Bob sees on the other side of the universe simultaneously when Bob makes a simultaneous measurement. Well, this contradicts the very notion that these photons existed before they were measured. Because if they did, then whatever photon B is, whatever Bob will see when he measures photon B, will be whatever it is, independent of Alice's choice of what to measure about photon A. And people came up with all kinds of possible loopholes that could explain this, like the photons are talking to one another, or the measurement instruments are conspiring to make exactly the right choices so it looks like the photons didn't exist. That's superdeterminism, which is like bizarre stuff. Flat out theoretical excuses for which there is zero empirical evidence. There are gazillions of parallel universes, according to Hugh Everett, the many worlds interpretation. So whatever you see, you don't fret about it because everything else happens in the parallel universe for which we have no experimental evidence. So unless you entertain what I would characterize as preposterous theoretical fantasies, completely devoid of reason and evidence, unless you entertain those, you have to accept that physical things are the results of measurement. But because a lot of scientists have the prejudice that only physical things can exist, then what is it that you are measuring? Physical things are the result of a measurement, and you surely measured something, otherwise there wouldn't be a result. What is it that you measured? And then they go bananas, and then they go like a physicist I respect, Carlo Rovelli, who basically says, well, it's turtles all the way down, you know? It's all relational stuff. There's nothing that is absolute, which is, of course, a cop-out. Because, you know, if relations are relations amongst relations, what are these meta-relations relations of? Meta-meta relations. So it's turtles all the way down, right? It's meta-meta-meta ad infinitum relations. If you do not have a metaphysical prejudice, however, what nature is telling us is staring us in the face. It's obvious. Physicality is a dashboard representation. And a dashboard only shows something when a measurement has been made, when sensors picked up something to be represented on the dashboard. If you don't measure anything, the dashboard shows nothing. There is nothing physical. The thing that is measured is not physical, and it's really there. And it's not physical in the sense that you cannot exhaustively characterize it through physical quantities like mass, charge, momentum, spin, all that stuff. It's just of a different order. What order? Do we have an example of that? Of course we have. The qualities of experience. What is the length in centimeters of your thought? What is the weight in kilograms of your emotion? You know, the experiential states that are not perceptual are not physical in the sense that they cannot be exhaustively characterizable through physical quantities. Obviously, that's what we measure. And physicality is the dashboard representation of the measurement that appears on the screen of perception. And even if we use instrumentation, like photodetectors, we only know the output of those instruments by perceiving them. So you're always filtering everything out through the dashboard, through perception. If physicists were not contaminated by a metaphysical prejudice, I think foundations of physics would be a lot saner today. But right now it is insane. It's worse than Star Trek. Superdeterminism and aberration multiverses, this is beyond science fiction. It's gratuitous La La Land stuff. So I think in practice, Francis, because scientists are humans and humans have prejudices, I think metaphysical sanity can change the practical advancement of science.
But what would that change? I mean, the experiment you were alluding to, you know, which is the APR paradox and the aspect and other experiments using
Alan aspect
using Bell's inequality. I think there are various interpretations to this, but one which seems to be the most convincing is that there are no local hidden variables. And in a sense, there still might be hidden variables in hand's pocket, in God's pocket or in God's hand, right? And only God knows what the measurement, the outcome of the measurement of the polarization of the photons or the spin of the electrons, if you do it with electrons, will be. But for us, it is not determined up until the photons are in flight, right? So,
well,
yeah,
we can go into more detail.
It's entanglement at a distance and instantaneous entanglement are faster than the speed of light. Basically, that's what it is. So we lose the locality principle somehow, part of it, and that's a problem for physicists, because we like to conduct experiments in isolated labs, and we like that the forces that act on our experiments diminish with the distance and can be neglected if the origin, the sources of these forces are far enough. So that simplifies our model, and that's puzzling.
Look, there's a lot of polemic about it, and it sort of came to a culmination in 2022 when the Nobel Prize in Physics was given. Some would argue that the original inequalities by John Bell, they worked as a sort of an exclusion theorem. In other words, you cannot have physical realism and locality at the same time. Physical realism meaning that what you measure are physical entities that have standalone reality. That's physical realism. And locality is all causal interactions have to be local. You have to have a causal chain over a distance, a chain of causal local interactions. And the original interpretation was, I'm not sure that's quite correct if you look at the math, but in general terms, people would say, well, proving Bell's inequalities, proving that they exist, means that you cannot have locality and physical realism at the same time, but you can pick and choose. So if you give up locality, you can still hold on to physical realism. It's just that the hidden variables are global, a kind of cosmic conspiracy. But then, and that's how this thing went, since Alain Aspect started in 1979 and then he refined his experiments in 81 and 82, published a number of papers. Then in the 90s, there were much better experimental confirmations of Bell's inequalities in Austria and Switzerland in the late 90s. But then in 2003, a physicist who I believe is still alive, Anthony Leggett, he published a paper in the journal Foundations of Physics with new inequalities, Leggett's inequalities. Importantly, some of those inequalities made a distinction between locality and physical realism. If some of those inequalities were correct experimentally, then you had to exclude realism, even if you had already given up on locality. You couldn't pick and choose. You would have to exclude realism, meaning physical entities do not have standalone existence. They arise from measurement. What you measure is not physical, in the sense of not being exhaustively describable through physical quantities. And lo and behold, in 2007 and 10, Leggett's inequalities were shown experimentally to hold. And then the only class of interpretation that could survive that and still be physically realist was something along the lines of Brownian mechanics, pilot wave theory. But of course, the problem is that, well, there are many problems with pilot wave theory. It does not have a relativistic extension because it doesn't deal in fields. Yeah. It deals with discrete entities. So you can't reconcile it with special relativity. And therefore, you cannot reconcile it with quantum field theory. And arguably, any interpretation of quantum mechanics, classical quantum mechanics, that is at all reconcilable with quantum field theory would have this interpretation of particles as excitations of a field and not as little balls, little billiard balls, like in the original Bohmian mechanics interpretation, which actually is Louis de Broglie's interpretation.
Yes.
But Louis
yes.
Yeah, but Louis himself gave that up like 100 years ago. And David Bohm picked that up again after Louis de Broglie had given up on it. And David Bohm picked it up again in the early 50s, published a 2-part paper, very long, in 1951, proposing this. But there are so many reasons why it's not viable. And if you bite that bullet and you say, okay, Bohmian mechanics is not valid, then realism, physical realism, is out of the picture. It's not only, you can't just choose anymore to abandon locality, but hold on to physical realism. And the way to get out of it now, if you really want to be a physical realist, there are 2 ways. One is Everest and many worlds, which is probably the most inflationary idea in the history of thought. You cannot get more inflationary. And basically it says everything that can happen does happen in some parallel, inaccessible universe. Or superdeterminism, which is a cosmic conspiracy theory. Like an act of measurement changes what's measured, and it changes it in such a way, instantaneously and across arbitrary distances, that the two detectors conspire to create the illusion of entanglement. I mean, if you believe that, what do you not believe, right? So I think that's the state of play today, in my view.
I didn't follow with this Liggett experiment or inequalities that you suggested. I didn't follow how it can make the determinations between
realism,
global realism, not atomistic realism, but global realism and idealism. I don't see how.
Well, not idealism. It doesn't make a metaphysical prediction. It just tells you that it's not enough to abandon locality to hold on to physical realism, because certain statistical properties that, if verified experimentally, would contradict even realism under non-local assumptions, except for one particular category of global realist theories, a la Bohmian mechanics. So that one is not excluded. Pilot wave theory is not excluded. But there are so many other reasons to not take pilot wave theory seriously. I mentioned only the biggest one, which is it is not a field formulation. It cannot reconcile it with relativity or quantum field theory. And if you can't do that, then you can't explain particle interactions, because original quantum theory doesn't say anything about interactions. You cannot explain particle decay. You cannot. You do not have the Higgs. The entire Higgs mechanism of inertial mass. You don't have it anymore, because that's a field formulation, right? The Higgs field is the sticky field that creates. Yeah. So many things would become impossible if you take that particular class of interpretation seriously. So in my mind, the conclusion is, no, what you measure is not physical. Physicality is a measurement representation on a dashboard. But because all we have is a dashboard, we don't have a transparent window to see the world as it actually is. We think that the only thing that exists is dashboard stuff. And that's a metaphysical prejudice. I think science should be the science of science should be the activity of trying to accurately predict what will happen next.
That's what it is. Basically, it's a question of motion, right? So that's what it is. It's trying to. It's not to say what the thing is, but how the thing behaves in a controlled as possible environment. That's a goal, but I don't think that science has anything to tell us about ontology, and I don't think that ontology has much to tell us about science, as science is currently conducted. science, it has right now has lost its momentum. Since the Standard Model and general relativity, not much has been achieved. Experientially, yes, the Higgs field being proven experientially, that was a major achievement. But other than that, and this quantum field theory is interesting, but at the same time, not very satisfying. I mean, QED works fine, but regarding the weak and strong force and the coupling constant, ideally, we should be able to calculate that from first principles, right?
Yeah, we're not there yet. Yeah,
a lot needs to be achieved in that sense, and string theory is way too big.
Yeah, it's over-determining. Sorry, it's under-determining. Yeah,
determining, yes, to fit our and we don't know, and it seems that we don't know where to go. Quantum loop theory is not very convincing either. I've read Carlo Rovelli's book, and I mean, some young guy will come at some point and break. I think one of the problems is that we don't have a convincing interpretation of QM. I found interesting the consciousness-based interpretation that von Neumann suggests in his book Grundlage der Quantenmechanik, where it shows that no matter where you draw the line between the measuring apparatus and the system you are measuring, it doesn't matter, right? So
it's
that
just entangled, yeah.
So that you can ultimately choose to draw the line at consciousness. And of course, this notion is abhorrent to most physicists, because since they construe consciousness as being anthropocentric, it's abhorrent, and rightfully so. But if you are open to the possibility of universal consciousness, it kind of changes.
Absolutely.
Changes the possibility of the interpretation.
Yeah. Yeah, because under physicalism, consciousness causes collapse attributes to human consciousness the magical power of instantly changing the entire universe at a glance, right? When you look up to the sky, you collapse the state of the entire universe. And that's why it's so abhorrent. But as you said, if you don't think of consciousness as a human thing, and you don't think of the universe as something ontologically distinct from consciousness, then consciousness has no magical power. It's just what there is. And prior to collapse, this is another grievance of mine. And bear with me, I don't want to overdo on this, but in physics there is this tendency by many to think of the wave function, Schrödinger's equation, as ontic, as something that really exists, that is really out there, as opposed to the best model we apes have come up with.
Everything is a model. Everything is a model.
Yeah, but there are people, and I had a discussion a few months ago with Sir Roger Penrose, in which, for him, it's self-evident that collapse exists. And when I started questioning it, I said, I think collapse is epistemic. It's not a process that is happening out there. It's just that we have limited knowledge at one point, but when we observe, we have complete knowledge or certain knowledge. And he was saying, no, the collapse really happens because obviously something has to change the wave function into a defined reality.
In a sense, it's true, because before we measure, let's say, the spin of the electron, it is actually in a superposition, or before we measure the polarization of the two photons in the EPR experiment, it is truly in a superposition, right? That we know.
It's our model, right? What you could say is that in interference experiments, when you see an interference, you call that an empirical evidence for a superposition. Say in the double slit experiment, if you see the interference pattern, then that represents some kind of superposition, you could say. But Schrödinger's equation, I think, and I am with Chris Fuchs and the other cubists on this, which is another interpretation.
Yes, a Bayesian interpretation.
Bayesian quantum mechanics, yeah, which basically says the wave function is just a model of what we know. It's our betting strategy. It's not something that is out there. What is out there is sometimes we see an interference, but we go too quickly into that translation between the empirical reality of an interference pattern on a screen or a measurement surface to saying, oh, the world is actually in a superposition until we look. I think, yeah, there's too much. It's too big a step, I think. In my naive view, Francis, the wave function is the best model we have, and it's not complete. That's why we can't predict the outcome of single quantum observations. But it doesn't mean either that single quantum observations are random. Of course, they are not. Otherwise, there would be no law of large numbers. They would obey no precise statistical distribution as they do. So I'm not one of those who says, consciousness magically collapses a superposition state. I'm more cautious. I don't have a definite opinion on this. I think everything is conscious processes or conscious states. Everything, we, the world, everything. The world is just the appearance upon measurement of patterns of excitation of this subjective field that nature is. But how that precisely relates to quantum mechanics, I'm not confident enough to make a final pronouncement. I did write a paper and published a paper in Philosophy and Cosmology, very detailed about this back in 2017 or 18. But it doesn't solve the measurement problem. It just argues that it's much easier to interpret quantum mechanics if we part with the prejudice that the thing measured is of the same nature as the measurement result. The measurement result is what appears on a dashboard. You can characterize that with physical quantities because we created physical quantities to characterize the dashboard. But to insist that the thing that is measured is dashboard-like, I think it's a prejudice that is unnecessary and makes things complicated. But, final theory of everything, I don't think we are nowhere near that.
Yeah, we cannot. We are navigating in the clouds, in instrument flying roofs, and we have only access to the dashboard, right? And what is out there is just a theory, and we have to find the theory that gives us the best interpretation of what we see on the dashboard, and the correlation between the various observations we make on the dashboard. We have theories about what is behind it, right? And the best theory is the one that accounts for the largest number of observations we can make on the dashboard.
I agree. And I would add just one thing. We have to remain alert to the fact that a theory that makes good predictions proves the accuracy of the predictions, but not necessarily the reality of the theoretical entities that it employs to make the prediction.
Yes.
In other words, many theoretical entities are convenient fictions, like the convenient fiction of gravity being an instantaneous force that acts at a distance. It was very convenient to put a man on the moon. We used Newton's gravitational law to do that, but we know it's not true. There is no such a force. Now we think it's the twisting and bending of the fabric of space-time, another theoretical entity. And now look, quantum gravity is coming around and saying there is no such a thing as the bending and twisting of the fabric of space-time, because time is emergent, it's not fundamental. So our our convenient fictions change over time. What makes them...
Leonardo, there is something different about the scientific progress. It is true that they change, they evolve, but the new theory includes the previous theory as a less precise model and as a more limited model, but it's still valid. It doesn't invalidate. It refines and enlarges the previous theory. So that's something different from the magical mind, for instance, or for other views about nature. That's the power of science, is that it doesn't deny itself the next moment. It just improves.
Yes, yeah, I am with you completely there. Relativity, for instance, allowed us to predict the orbit of Mercury much better than classical Newtonian mechanics would have allowed. So I agree, there is a progress towards better and better and better predictions. I think the error we should not make, however, is to mistake convenient fictions for realities. In other words, in the time of Newton and all the way until 1905, the world behaved as though there were such an invisible force that acted at a distance. That was a convenient fiction until a certain point, but it couldn't predict the orbit of Mercury very well, so we threw away that convenient fiction and we adopted another one. And now, as far as we can determine, the world behaves as though there were this objective bending, twisting fabric of space-time. We even measure gravitational waves recently. So that's the current convenient fiction that makes better predictions. There will be a point where we will need another convenient fiction to make even better predictions. So what I'm insisting on is that we regard theoretical entities as convenient fictions. In other words, as far as we know, nature behaves as though there were a fabric of space-time, there were 17 quantum fields, and there were particular classes of patterns of excitations of these fields that correlate to the elementary particles in the standard model. Nature behaves as though there were virtual particles, force-carrying particles, and all that stuff. But we have to keep in mind that these are ways in our imagination in terms of which to think, so to make proper predictions. But what is ultimately valid is the prediction, not the way of thinking about them. The way of thinking about them is convenient. It gives you a good handle on how to do things, but it's convenient fictions. And the universe behaves as though they were true up to a certain point. But you have to learn to get rid of them and adopt new convenient fictions and think in a different way.
There must be something deeper behind these virtual particles. They remind me a little bit of the virtual forces that are used to explain Hamiltonian mechanics.
That's what I mean.
You see, I think what I find interesting in the quantum field theories are the symmetries, the gauge symmetries.
Yes.
And the fundamental, so that this kind of geometrical approach, the gauge fields, gauge bosons, all these things. It's a remarkable simplification. You have 1 cross S, you have 2 cross S, you have 3. It's a remarkable achievement.
It reveals something that must be fundamental at some level, right? That's what you're hinting at.
Points at something deeper, at something deeper. And this unification of physics is a work in progress. And it is not necessarily achieved by more simple equations. Quite the opposite. If you take the Einstein equations, in the form of it's a little more complicated than F equals ma.
Yeah.
But at the same time, it explains so much. You have the black holes in the spherical solutions. You have the expansion is the cosmological constant in the spherical equation, and in the linearizations in empty space, you have the gravitational waves. I mean, these three elements derived from Einstein's equation are remarkable. And we have an interpretation, unlike quantum mechanics. We have an interpretation. The problem is that it is based on continuous framework. The R13 space-time is continuous. And my guess is that in nature, there is only one thing which is truly continuous, which is the background of awareness, background of reality.
Yeah, I agree.
Everything else has at some point to be discrete. And that creates very difficult mathematics, because we have calculus, or we have differential geometry in the case of the Ricci tensor and the Riemann tensor and all that stuff, and the Christopher symbol. But it's already complicated enough with all these second-degree differential equations. But I don't know what I was going to say.
No, I follow your intuition, and I resonate a lot with it, because that's my inner disposition. When I was at CERN, I was like 22, 23 years old, and I thought, extending the gauge symmetries and going into supersymmetry, I thought that was so beautiful. We had to find supersymmetrical particles, right? Because it was so beautiful, so elegant. Nature had to be like that. It could not be like that, right? It had to be like that. That's a very Platonic disposition, beauty is truth. Truth and beauty are the same thing. We didn't find them. We didn't find the supersymmetrical particles at CERN. And those who still hold out hope expect that maybe we'll find them at a much higher level of energy. But then that starts becoming very inelegant. Then the whole motivation for it starts going away. So that was, for me, the first time the world hit me with a 2x4 on my face, denying my natural dispositions, my natural intuitions. Beauty is truth. And then learning about the history of science later on, as a more grown-up adult, you realize that the whole history of science is the history of the abandoning of convenient fictions. Now, there was a time when we thought that when we observed electrostatic attraction, if you would rub a piece of amber on a cloth, it would attract chaff, the peeling of wheat, and it just attracted it sort of magically, invisibly. So people postulated effluvium. Effluvium was supposed to be this elastic substance that connected amber to chaff. So when an electrostatic attraction would be explained in terms of that substance, that elastic substance, just receding and pulling the shaft towards the amber. And it was an invisible substance, and you could run your fingers through it, you wouldn't feel it. Well, we have another model now, right? The buildup of static electric charges. And that explains not only electrostatic attraction, but also repulsion, which effluvium couldn't explain. But the whole history of science is sort of this continuous replacement of convenient fictions, this enormous centuries-long lesson that our predictions are based on things that nature behaves as though those things were true, but they are not necessarily true in themselves. There is always an next better convenient fiction. So though I still hold out that intuition, you do hold out that there is some kind of steady progress. We are getting closer to something more fundamental here. There seems to be a clear gradient, a clear direction. We are not bouncing around in Brownian movement. We are replacing convenient fictions, yes, but they seem to get more and more refined. maybe the 17 quantum fields are the most refined yet. It would be nicer if we had one instead of 17, right?
But what I find interesting in this regard is the impact that the evolution of science has on philosophy, because it cuts both ways. Historically, people like Copernicus or Galileo already had an impact on the models that were promoted by the church. But quantum theory really, in my view, put an end of the atomistic realism theory, and Einstein also, with special relativity, seems to have put an end to 19th century views of time and space as being separate
entities or
whatever, separate realities. So and being absolute. So that there is no going back. It's irreversible, right? And that has an impact on philosophy.
Absolutely. I think, our original Democritean intuition that at the bottom level of reality, there are these little solid things with different shapes. That's gone, right? The closer we look, the more nothing we find, the more pure abstraction we find. It's like it never becomes more concrete. It only becomes less and less and less and less concrete. So yes, this has an impact on philosophy. Yeah.
You know that Richard Feynman was asked, what is, in your view, the most major intuition in science? And he said precisely this one, the atomistic hypothesis of Democritus. And I found that a little weird because it doesn't jive with QFT, right? That much.
No, QFT would deny that there are these little things. They are just metaphors.
But the king of QE, of quantum
dynamics, which was the beginning of QFT.
To say that,
Yeah. No, well, you could say Feynman was the father of QFT because QED is just the first field formulation for the Dirac field, but for all the other fields, they are similar formulations as well.
Dirac and Maxwell.
Yeah. So I share your intuition, but there is this disappointed idealist scientist in me. Idealist in the sense of ideals. Beauty is truth. So SUSY has to be true. Supersymmetry has to be true. And then after years, realizing it's not there.
We will. I have hope we will rediscover that. The beauty of the spin-off fields of Dirac. At the same token, discovering the antimatter, the positron, and at the same time the spin being delivered by simply the factorization of a sum of 5 square using Dirac matrices, right? So there is great beauty, there, great intuition. You're looking for a linear version of the Klein-Gordon equation. So
it's just not the beauty I thought would be there. It's a different kind of beauty. But I did find beauty that is true, so beautiful that it brought me to tears. When I first understood Euler's equation.
Which one?
Euler's equation that relates E, pi, I, all the mathematical constants.
Minus 1.
Yeah, exactly. Minus 1 equals 0. When I understood Euler's equation for the first time, I teared up.
No, it's plus 1 equals 0.
Correct. Plus 1 equals 0. Yeah. I teared up because I knew how those constants were derived, right? I came from completely different mental space and pi. Now, why would they come together in that way? And I still get, how do you say it in English, when your hair follicles go up? And I still get that when I think of Euler's equation. It's like, how is this possible that this is true? It is true. You can follow the demonstration. It's undoubtedly true. But how? How is it possible? How can this be true? Right? So that reassured me. But as a young man, we were looking for SUSY desperately. Supersymmetry. That's why we were doing what we were doing. Then the Higgs boson would be there. Then everybody knew it would be there. You know, it had to be there. It was too neatly predicted. And there were some events we had seen before with the LEP that were consistent with the Higgs boson, just didn't have the statistics. You couldn't go 3 sigma. But supersymmetry is what I was doing it for. And that's the biggest disappointment of my young scientific career. It's not there. And it took me a while. It took me into the pandemic to really accept that. Because I kept thinking, wow, now they'll increase the energy of the LHC. They did that, I think, 2016 or 2015. They shut it down and they brought it to a new energy level. And I thought, now they will find it. No. It's not there. And yeah, it's so bloody disappointing because I was a kid at the time. And I was not a cynical adult that parts with old ideas very easily. That hit close to my heart.
Something must give. Like after the Michelson-Morley experiment, Einstein view that the speed of light is the same in all frames of reference. You know, that seals the deal. It's thinking out of the box. Something will come up.
Yeah. I think you're very correct in your initial assessment that true scientific progress has stopped fundamentally around the 1920s, but we managed to sort of elaborate on that until the 60s with the Standard Model. But true scientific revolutions ended with quantum mechanics and general relativity. They have to happen again. But it's very difficult now that science is just a job with performance appraisals at the end of the year and publish or die and all this stuff.
And there is something fishy I find with quantum field theory, is that one of the reasons why, in my view, quantum electrodynamics works well is because the second quantization, we are quantizing basically a real field, which is the electromagnetic field.
I see where you're going with it.
Whereas the rest, the second quantization is a quantization of the wave function. And the wave function, of course, is a field, but it's not a real field.
Yeah, but some of the other fields are pretty concrete in the sense that we can measure the particles that betray their presence. In the Higgs field, for instance. I mean, we have to be careful here. We never measured the Higgs boson. That's a misunderstanding that most people have. The Higgs boson decays too fast. It doesn't interact with any measurement surface. What we measure are the particles the Higgs boson decays into, and then we can sort of reconstruct that retroactively. But there is this bump in the energy histogram, more or less precisely where Peter Higgs predicted there should be the boson. And that's pretty concrete evidence that there is such a thing as a Higgs field. And some of the other fields are fairly concrete as well.
It's very interesting. There is no other way to do it, right?
Now, if the field's not excited, it doesn't...
Because the particles have to be massless, because of the symmetries up until they interact with the Higgs field.
Correct. Everything would be going at the speed of light without the Higgs field. As far as inertial mass is concerned, there are other mechanisms from mass, which are not, for instance, the mass of a baryon, like a proton with the the three quarks and the gluons moving inside. Very little of that is actually from the Higgs field. It doesn't matter. This is detail. A lot of stuff that we take for granted can only arise. We can only understand its existence by assuming the reality of this very convenient fiction called the Higgs field. So from that perspective, it is concrete because there is some...
It's a beautiful mathematical substitution.
The mathematics of the standard model works extraordinarily well. It really is really neat. It's just that it doesn't explain everything. There is stuff that is out of scope. Some existing problems in physics that and moreover, it can't be reconciled with general relativity.
Yes, and we didn't even mention the problem with the infinities, which have to do with the continuous model, you know, of the equation versus
the discreteness of empirical reality, right?
The discrete, perhaps inherently discrete nature.
Yeah, no, there are some who would argue that the discreteness of space-time is a theoretical inference. Because, you know, the Planck scales, we say we cannot go below that because the math gets all crazy. It's like there are little black holes below the Planck scale in space. But we don't really know if it's really discrete. You know, it's just that the math sort of breaks down, becomes really weird. The Planck scale, you cannot weave a coherent chain of causality below that, which doesn't mean that there is nothing there. I mean, who knows?
There are little black holes.
Who knows? Who knows? Things have gotten very strange already. Who knows whether you will stop being very strange?
And we are kind of also in a black hole with this acceleration of the expansion of the universe, you know, the cosmological constant and dark energy, because at the edge it accelerates faster than the speed of light, so we cannot send signal outside, right? So we are ourselves already in a black hole. So we are in a black hole. All right, we cannot exit, and we cannot penetrate the black holes which are inside.
Beyond it, we cannot see anything beyond the cosmic horizon. But you see, some convenient fictions are very elegant, and then I share your intuition. They must be telling us something. But other convenient fictions are profoundly inelegant, and the cosmological constant, in my view, is a profoundly inelegant convenient fiction. It's a hack. It's just, well, things seem to be accelerating more than we thought they should be. So we just drop a term, brute force, in that equation.
Yes, you have R mu nu minus 1/2 of G mu of R G mu nu. And then he says, okay, yes, but we could add a constant instead of a scalar. And, okay, plus lambda G mu nu. So, but...
They fine-tuned that through observation. So they calibrated exactly...
He wanted to be, and I mean, Einstein wanted to be thorough and not to neglect any possibilities, right? So he put that.
And we are holding on to it because observation suggests that things are accelerating. The expansion is accelerating, and it shouldn't be.
And we don't have a better model as far as I know.
And even by using the cosmological constant, we can create these very large-scale models of the universe and calculate where dark energy, or cosmological constant, where dark energy is distributed. And the result of that is that the whole thing looks like a neural network, which is suggestive. It's very interesting. I grant them that. But the scientist in me is still very hopeful that we will find out some principles that explain the observations as opposed to just brute force dropping something in to do the work. I find that almost irksome. There was a paper recently, it doesn't really work for everything. It works only on a specific set of observations, but it's it's interesting. When we calculate the expansion of the universe using normal models, we assume that time is passing at the same rate everywhere, which we know is not true, because depending on the presence of mass and energy, time goes lower or quicker, right? So in these big voids in the universe, time goes at a different rate than when it's in the middle of a cluster. And we just assume that these effects average out. But if you don't assume that, could you have an observation artifact, which is not there, it's just an artifact that would look like the universe's expansion is accelerating? And they made the case that, yes, that's what it would look like if you didn't take into account that time goes at different rates depending on the distribution of mass and energy in the universe. It doesn't work for some other reasons, but this is what I would like to see. Instead of a hard drop of a cosmological constant, which I find a hack, some reasoning from first principles out of which the rate of expansion emerges, as opposed to sort of a retroactive hack of the model to massage it into fitting the observations. You see what I mean?
Yes, and also, we always look for simplicity. We always look for linear solutions or linear equations, right?
And new ones.
And even Einstein's equations, there are many more equations that could be more complicated, right? He just chose and to choose as simple, to go as simple as possible. But there is no guarantee that the universe is subjected to linear equations, right?
There's no guarantee the universe is subject to anything apes can come up with.
And that's why perturbation theory, for instance, has its own limits, right? Because it's valid only when...
In the linear regimen, yeah.
The linear regimen, exactly. So, and also, the part of the universe which is inaccessible to us for the reason we explain, it's humongous.
Yeah.
So it's like if you look at a tiny city on the surface of the earth and look at what the municipal laws are in effect in these cities where you live, you cannot from that infer that the same laws are in effect all over the world.
Yes.
I was reading you were mentioning Roger Penrose, and I like very much his book, Reality, the thick book. And I don't remember what are the odds, 10 to the I don't know how much, compared to our accessible universe, what is out there. And so as a result, there is no guarantee that the laws extend into space-time way beyond our little.
Maybe the universal mind has a very fertile imagination, and who knows what it's imagining elsewhere. True. I don't know a lot, but there are scientists out there who would say, no, the laws of nature are stable and the same everywhere. And the reason they say that is that they have these cosmological models that assume that the laws of nature are the same across time and space. And then they calibrate it to observations, and then the model gives the universe we see today. They don't realize that there is question begging in there, right? You make an assumption, and then you calibrate the model so the assumption works. It doesn't mean that the assumption was correct. You made it correct, right? So yes, I am with you, and I may be against the mainstream that we don't have strong reasons to think the laws of nature are the same everywhere. Nature's imagination can be infinite.
Ultimately, the scientific endeavor is a game, right?
Of course.
And we shouldn't be we shouldn't take it too seriously ultimately.
It's a useful game for the production of toys, such as the computers we are using.
And for the scientists, it's a playful game to play, and the engineers produce toys.
Yeah, which is what I'm doing these days, producing toys. Anyway.
I don't know. I think I have to go.
I have to go too. I have to have my girlfriend is calling me already.
I don't know what we do with this.
We just published.